Analyzing algorithms. Analyzing an algorithm has come to mean predicting the resources that the algorithm requires. What does analysis mean? Occasionally, resources such as memory, communication bandwidth, or computer hardware are of primary concern, but most often it is computational time that we want to measure. Generally, by analyzing several candidate algorithms for a problem, a most efficient one can be easily identified. Such analysis may indicate more than one viable candidate, but several inferior algorithms are usually discarded in the process. Before we can analyze an algorithm, we must have a model of the implementation technology that will be used, including a model for the resources of that technology and their costs. For most of this course, we shall assume a generic one processor random access machine model, which is the RAM model of computation, as our implementation technology, and understand that our algorithms will be implemented as computer programs. In the RAM model, instructions are executed one after another with no concurrent operations. Strictly speaking, one should precisely define the instructions of the RAM model and their cause. To do so, however, it would be tedious and would yield little insight into algorithm design and analysis. The RAM model contains instructions commonly found in real computers: arithmetic, add, subtract, multiply, divide, remainder, floor, ceiling, data movement, which includes load, store, copy, and control statements like conditional and unconditional branch, subroutine call, and return. Each such instruction takes a constant amount of time. When working with inputs of size n, we typically assume that integers are represented by C log n bits for some constant c greater than or equal to 1. We require c greater than or equal to 1 so that each word can hold the value of n, enabling us to index the individual input elements, and we restrict c to be a constant so that the word size does not grow arbitrarily. If the word size could grow arbitrarily, we could store huge amounts of data in one word and operate on it all in constant time, which is an unrealistic scenario. Analyzing even a simple algorithm in the RAM model can be a challenge. The mathematical tools required may include combinatorics, probability theory, etc. Now, let us look at an example of insertion sort to understand the analysis of algorithms. The time taken by the insertion sort procedure depends on the input. Sorting 1,000 numbers takes longer than sorting 3 numbers. Moreover, insertion sort can take different amounts of time to sort two input sequences of the same size, depending on how nearly sorted they already are. In general, the time taken by an algorithm grows with the size of the input. So, it is traditional to describe the running time of a program as a function of the size of the input. To do so, we need to define the terms running time and size of input more carefully. The running time of an algorithm on a particular input is the number of primitive operations or steps executed. It is convenient to define the notion of step so that it is as machine independent as possible. For the moment, let us adopt this view. A constant amount of time is required to execute each line of our pseudocode here. One line may take a different amount of time than another line, but we shall assume that each execution of the ith line takes time ci, where ci is a constant. Our expression for the running time of insertion sort will evolve from a messy formula that uses all the statement cos Ci shown here to a much simpler notation, which is more concise and more easily manipulated. We start by presenting the insertion sort procedure with the time cost of each statement and the number of times each statement is executed. As you can see, for each j is equal to 2, 3, so on till n, where n is equal to length of a, we let tj be the number of times the while loop test in line 5 is executed for that value of j. When a for or while loop exits in the usual way, that is, due to the test in the loop header, the test is executed one time more than the loop body. We assume that comments are not executable statements and so they take no time. The running time of the algorithm is the sum of running times for each statement executed. A statement that takes Ci steps to execute and is executed n times will contribute Cin to the total running time. To compute T of n, the running time of insertion sort, we sum the products of the cost and times columns and we obtain this formula. T of n is equal to C1n plus C2 into n minus 1 plus C4 into n minus 1 plus C5 sigma j is equal to 2 power n Tj plus C6 sigma j is equal to 2 power n Tj minus 1 plus C7 sigma j equal to 2 power n Tj minus 1 plus C8 into n minus 1. Even for inputs of a given size, an algorithm's running time may depend on which input of that size is given. For example, in insertion sort, the best case occurs if the array is already sorted. For each j is equal to 2, 3, so on till n, we then find that a of I less than or equal to key in line 5 when I has its initial value of j minus 1. Thus, Tj is equal to 1 for j is equal to 2, 3, so on till n. And the best case running time is T of n is equal to C1n plus C2 into n minus 1 plus C4 into n minus 1 plus C5 into n minus 1 plus C8 into n minus 1, which when simplified gives C1 plus C2 plus C4 plus C5 plus C8 into n minus C2 plus C4 plus C5 plus C8. This running time can be expressed as an plus b for constants a and b that depend on the statement cos Ci. It is thus a linear function of n. If the array is in reverse sorted order, that is, in decreasing order, the worst case results. We must compare each element aj with each element in the entire sorted subarray a1 to j minus 1, and so Tj is equal to j for j equal to 2, 3, so on till n, and we can note that sigma j is equal to 2 to n, j is equal to n into n plus 1 by 2 minus 1, and sigma j is equal to 2 to n, j minus 1 will be equal to n into n plus 1 by 2. We find that in the worst case, the running time of insertion sort is T of n is equal to C1n plus C2 into n minus 1 plus C4 into n minus 1 plus C5 into n plus 1 by 2 minus 1 plus C6 into n minus 1 by 2 plus C7 into n minus 1 by 2 plus C8 into n minus 1, which gives us C5 by 2 plus C6 by 2 plus C7 by 2 into n square plus C1 plus C2 plus C3 plus C5 by 2 minus C6 by 2 minus C7 by 2 plus C8 into n minus C2 plus C4 plus C5 plus C8. The worst case running time can be expressed as an square plus bn plus c for constants a, b and c that again depend on the statement cos ci. It is thus a quadratic function of n. Typically as an insertion sort, the running time of an algorithm is fixed for a given input. Although in later lectures, we shall see some interesting randomized algorithms whose behavior can vary even for a fixed input. Now let us look at worst case and average case analysis. In our analysis of insertion sort, we looked at both the best case in which the input array was already sorted and the worst case in which the input array was reverse sorted. Though we usually concentrate on finding only the worst case running time, that is, the longest running time for any input of size n, we give three reasons for this orientation. The first one is the worst case running time of an algorithm is an upper bound on the running time for any input. Knowing it gives us a guarantee that the algorithm will never take any longer. We need not make some educated guess about the running time and hope that it never gets much worse. Then, the average case is often roughly as bad as the worst case. Suppose that we randomly choose n numbers and apply insertion sort. How long does it take to determine where in subarray A1j minus 1 to insert element aj? On average, half the elements in A1j minus 1 are less than aj and half the elements are greater. On average, therefore, we check half of the subarray A1j minus 1. So, Tj is equal to j by 2. If we work out the resulting average case running time, it turns out to be a quadratic function of the input size, just like the worst case running time. One problem with performing an average case analysis is that it may not be apparent what constitutes an average input for a particular problem. Often, we assume that all inputs of a given size are equally likely. In practice, this assumption may be violated, but we can sometimes use a randomized algorithm which makes random choices to allow a probabilistic analysis. We use some simplifying abstractions to ease our analysis of the insertion sort procedure. First, we ignore the actual cost of each statement using the constants Ci to represent these costs. Then, we observe that even these constants give us more detail than we really need. The worst case running time is an square plus bn plus c for some constants a, b and c that depend on the statement cos ci. We thus ignore not only the actual statement cos but also the abstract cos ci. We shall now make one more simplifying abstraction. It is the rate of growth or order of growth of the running time that really interests us. We therefore consider only the leading term of a formula an square, since the lower order terms are relatively insignificant for large n. We also ignore the leading term's constant coefficient, since constant factors are less significant than the rate of growth in determining computational efficiency for large inputs. Thus, we write that insertion sort, for example, has a worst case running time of theta n square. We usually consider one algorithm to be more efficient than another if its worst case running time has a lower order of growth. Due to constant factors and lower order terms, this evaluation may be in error for small inputs. But for large inputs, a theta n square algorithm, for example, will run more quickly in the worst case than a theta n cube algorithm.